we've been doing related to building life cycle assessment, and particularly with an emphasis to try to support building design decisions. My name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub and also one of the lead researchers on this particular topic, which is also being done by a whole team of researchers here at MIT. Part of the motivation for our work is that there's a real increased demand for green buildings, and this is showing a chart here for U.S. single-family housing green market and some projections done by a McGraw-Hill construction estimate, and it shows really significant growth in the housing space. Here's another chart that's been provided by the U.S. Green Building Council showing national lead construction spending, and actually the rate at which the green building industry is growing is faster than non-green construction. And one of the interesting things about what's driving this demand, and this once again comes from the McGraw-Hill construction study, is that client demand is one of those key drivers, whether it's in the U.S. or global. So clearly there's a lot of demand for green buildings, but you know, we still have a question about what does it mean to be green, right? People say they want a green building, but how do you quantify that? And we can actually draw some inspiration on this particular topic from another study that was done by UL, and they call it the sins of greenwashing. And it's a little bit out of date now, but I think the premise still holds. It's more about consumer products, but what they did is they did a study of many different types of products across a variety of sectors, whether it be electronics or office products. And basically, they in 2009 they found about 2,700 products that claimed to be green, and then in 2010 they found an increase even more, 4,700 or so. And what they did is they characterized whether or not these supposed green products had actually made claims that could not be justified, and they characterized these as having 7 different sins of greenwashing, and this is showing a chart that's in the do-it-yourself building or construction sector, so not quite what we're going to be talking about, but also this is more like places like a Home Depot or things like that. And without going into a lot of the details, they basically found that pretty much all of the green products make at least one claim about them being green that may or may not be true. And so sometimes it's just no proof, but sometimes it could be they have a label that there isn't justification. So clearly this is a hard thing to be able to determine what does green mean. And actually one of my favorite examples is biodegradable trash bags. And, you know, they make it really hard for you to think that they're not green because obviously the bag itself is green. But of course, the challenge is that if you put a biodegradable trash bag into a landfill, first of all, it probably won't degrade that much. And if it does, it actually will likely turn to methane, which is worse than carbon dioxide when it comes to climate change. So this is tricky. One of the good things about what UL does, though, in trying to say how to address this, be honest about the whole life cycle-based environmental impacts of your products. Acknowledge them and address them one step at a time. And I really like that, and I think that's been a core part of what we're trying to do as well. You just analyze the whole life cycle perspective and then see what you can do. And this life cycle perspective is really important for these green claims. Because the reality is there's many mechanisms for reducing environmental impact and cost. And when we look across the life cycle of any product, people often will say, well, I have a green material because perhaps it used recycled content or it's low energy to produce. But there are other opportunities to have a green building, let's say in this case. If you can design a building to use less material, then i.e. by using a stronger material, then that can certainly help reduce environmental impact and possibly cost. The same thing with longer lasting designs. But there are other opportunities in the use phase, such as reducing energy consumption or heat island effects. And of course, anything that can happen at end of life, either by enabling material recovery or planning for component reuse, can be beneficial as well. The trick is that you really need to prioritize these mechanisms, and to do so, you have to really do a trade-off analysis of performance and life cycle environmental impacts and cost. And this is really important for us to talk about these things. Keep in mind that we are asking to have something built because we're looking for some kind of performance, whether it be just providing shelter or providing a working environment or a retail environment. But there are trade-offs about cost and environmental impacts. And so we want to look at all those things together. So when it comes to the research that we're doing at the Concrete Sustainability Hub related to building life cycle assessment, our objectives are going to be to identify what are the key drivers of building environmental impacts, what's the state of life cycle assessment in the building design process, and then try to support early stage building design decisions with quantitative life cycle environmental impacts. And the approach that we've taken to do this is to conduct some detailed life cycle assessments, and then we took a step back and then assessed more broadly the state of life cycle assessment, and then developed a streamlined life cycle assessment tool. So what I'm going to do in this presentation is spend time going into each of these different topics, starting with conducting a detailed life cycle assessment. So for those of you who may not be familiar with the concept of life cycle assessment, it's basically an approach by which we quantify environmental impacts of a product or a process from cradle to grave. So we start by looking at digging materials out of the earth and then transforming them into products that can be used to make, or materials that can be used to make different products, and using those products throughout their life, and then disposing of or recovering them at end of life. So it's really, they call it a cradle to grave or cradle to cradle process to quantify all those. And we can use metrics like greenhouse gas emissions to track those things throughout their life. So when it comes to the detailed life cycle assessments that we did in the Concrete Sustainability Hub, we looked at buildings in Chicago and Phoenix that were designed to code, and then looked at a couple different types of buildings. We looked at single-family homes and a multifamily building. And we looked at construction of each of those, either using wood frame construction or what's known as insulated concrete forms. So this is a concrete technology that basically the forms that are used to make the concrete are actually insulated blocks, and then those stay on site. And so this sandwich of insulation and concrete stays and basically provides then structural component for the building and also insulation. And we also analyzed a commercial office building constructed in both steel and concrete. And there's a reference here. This title is on our website, and we have a link to this, but that's also one way to be able to search for a lot more of the details. What I want to give you are just a high-level sense of what some of the results are. Like I said, we looked at the entire life cycle of these buildings, and one of the things that we quantified is the energy consumption of the buildings. And how you read this chart is the y-axis is global warming potential in pounds of carbon dioxide per square foot of the building. And global warming potential is just a metric primarily of the carbon dioxide that's associated with all these different processes. In terms of energy consumption here, this is basically generating electricity or using natural gas for heating. And what this is showing right here are the different wall construction types, either insulated concrete forms and wood for the single family and multifamily buildings, and concrete and steel for the commercial ones. And these are the different locations, and we chose those locations because they're different climates. And here's the different building types. So this chart is showing the energy consumption in those buildings over 60 years, so what we assume to be the lifetime of the building. So What's interesting that you can see is that generally, just by a little bit, it's on the order of, like 3 to 8% or so, the concrete structures have lower energy use. But what's also interesting now, if we look at the embodied impacts of the building. So the embodied impacts are basically the environmental impacts associated with making all of these materials and then doing the construction on site. So the embodied impact for the wood and steel structures is lower for them. Now, the key thing we want to look at is what happens when you combine both of those together. I didn't really get into the y-axis. And what you see is that this life cycle perspective is really important because the embodied impact is this orange part down here, and the energy consumption is this blue part here. So a key thing that we learned is that the energy use really dominates compared to embodied impact. So we want to look at that whole life cycle perspective together. Of course, what we also want to look at is what's the impact that these materials, the embodied portion, has on the energy use. All right, next topic. So our objective was then to say more broadly, what's the state of life cycle assessment in the building design process? And we did this through a couple different mechanisms. One is we reviewed the literature on building life cycle assessments to see what other people had published on this. 2, we did some studies to identify what are critical issues in conducting building life cycle assessments. And 3, we did some surveys of building designers. So I'll go through each one of those, starting with the first one. There's a study that's also on our website about this with a particular focus on residential buildings, but here are the key conclusions we learned from that literature review of residential buildings. 1, comparisons are difficult due to variation in scope. So for example, some studies will look just at the embodied portion, some will focus more on energy, some may include end of life, some they don't. So difference in scope makes it hard to compare across studies. However, one thing that's consistent that we see is that the use phase accounts for the majority of the life cycle impact in almost all cases. And what's also interesting, there's a particular interest in energy efficient designs, and what we see is that for those particular designs, there was significant variation in the fraction of the use phase to the total life cycle impact. So like if I put that in the context of the studies that we were just talking about, the ones that we did for different types of buildings, that use phase fraction was probably 80 to 90% of the total. And so that number we'll see has a particular variation. I'll show you a chart of that in a second. But what's interesting is that even though there is uncertainty associated with the lifetime of these buildings or other elements that are in the data, it's generally not considered. We've summarized this point about the use phase and its fraction of the total, and this is showing each data point here represents different types of designs that are in buildings that have been published in the literature. So these are not necessarily actual buildings, they're studies that were done on building designs. And the y-axis here is basically for that particular design, what did they report the percentage of the energy that's used in the use phase as a percentage of the total, right? And we plot that as a function of what's the assumed lifetime of the building, right? So for a longer lifetime, you would expect to have a higher fraction of energy consumption just because you make that investment kind of on day one in the embodied, but that is spread out over the whole lifetime, right? So the longer the lifetime, the smaller that is. But what's interesting, what we see is that there isn't necessarily really a clear trend. The different shapes here represent different types of buildings. And the NA, that means they didn't really specify whether it's energy efficient or code compliant, but as we can see, some of these, the blue ones, they're super energy efficient or energy efficient. Red means they're not code compliant, so even basically they might have a worse energy performance. And we do see a lot of those basically having the energy performance dominate. But even on some of these ones where they're considered to be energy efficient or super energy efficient, which one would expect the embodied portion of the environmental impact to have a higher fraction. You know, we're still talking, even in some of the best cases, 50-50, and here's one that's quite low in the 30s. So generally what we see, though, across most of these cases, we're talking, you know, 75% and higher, except for some outliers. So the key point there being that the use phase really dominates this life cycle impact, but you know, the exact amount depends on the particular case. So. Another thing that we did in surveying this whole field is basically after looking at the literature and spending some time looking at standards and things like that, we did a study that's down here called Comparing Whole Building and Building Product Environmental Performance. And it's actually, I should say, less of a study and more just basically our synthesis of what are the critical issues when comparing building environmental performance. And so what we wanted to do with this study was identify what are the critical issues in whole building and building product life cycle assessment, provide guidance for evaluating claims made between buildings or building products, because this is becoming something that people are much more interested in. Review, critique, and recommend current best practices related to those critical issues and best practices when it comes to life cycle assessment. And also investigate future best practices and offer suggestions for future standards and product category rules, which are the rules that are used to conduct a life cycle assessment when it's going to be used in an environmental product declaration, which is basically a summary of the environmental impacts for a particular product. So just at a high level, these are some of the critical issues that we found in the study. First of all, when it comes to system boundaries, it's really important to identify what are the boundaries and which life cycle processes are included, and then also to define what the reference study period is. That is, are you assuming the building has a 40-year life, 50-year life, 60-year, because that variation is significant. Then there's a lot of elements in what we call the analytical approach, basically how you do the calculations. And these are things that we think really there's an opportunity for either consensus or it's just important to be really transparent about this. So what's the criteria for functional equivalence? How do you do comparisons of different types of buildings? The location really matters because obviously that affects the energy consumption. The treatment of time really has to do with a lot of some of the elements, particularly around releases of biogenic carbon, which come from basically plant-derived or trees, and so that can be a critical issue. How uncertainty is treated, how allocation of different impacts is treated, particularly at end of life, and then how end of life is treated, operational energy, and biogenic carbon. So there's a lot more details in the report about what we mean by that, but essentially what we found is that until a lot of these things become either there's some more consistent definitions, it's hard to do comparisons across different studies. All right, last topic within this space is some surveys and focus groups that we did with architects. And we surveyed 16 architectural firms along with some home builders and developers. And then we did some focus groups in the Boston area with architects. And some of our key questions were, when in the design process are decisions being made? When do you choose specific windows or specific types of wall systems? Which tools are used throughout the process? And then what are the challenges to utilizing LCA? And the reference for this is also on our website, but it's a report. But some of the key findings that we had is that details are not available until late in the design process. So this right here is showing, how the design process progresses, starting with conceptual design, then schematic design, and then design development and construction documents. And this here is showing basically when are detailed decisions being made for different elements of the design. What you can see is that pretty early on, there's not a lot of details that are made. And so you get a lot of those details near the end of the process. And so that's going to have implications on how you do a life cycle assessment and based on when the data is available about what's being used in the design. So. All right, so what are the key findings of the surveys and the focus groups? A few things we found. One is that details are not available until late in the design process, and I just showed that with the previous chart. We also found that there was limited demand for life cycle assessment from customers, and so you combine that with the fact that LCAs were considered to be too costly or time-consuming, and it prevents the use of life cycle assessment much in the process. And so what that really means is that when we look at this design process, again, you know, your ability to influence performance actually happens early on in the design process, in the planning or pre-design or conceptual phases. That's when you can have the most impact. But of course, your cost of design changes increase as the time goes on, right? So what currently happens is that environmental assessments are done here because, as we showed, that's when a lot of the details are available. But as you might imagine, you can't really do much with that information because it happens at the end of the design process. So what we'd like to have happen is to shift this earlier in the design process, and even when details aren't available, we'd like to have feedback that accounts for that early design uncertainty. Because, of course, early on in the design process, you have a lot of design uncertainty, and that decreases as you go on and get more specific about what's in there. Fortunately, LEED has started to incorporate life cycle assessment into its process. The LEED standard, as probably many of you are familiar with, is trying to incentivize people to do green building by providing a rating system, and they have different categories for points. And within this materials and resources category, they have points that you can earn for either, I mentioned earlier, environmental product declarations, that is using products that have an environmental product declaration, which is like a nutrition label except about environmental impacts for something. And then they also have points for doing what they call a whole building life cycle assessment, which is basically where you do a life cycle assessment for all the embodied portion of the building. So while on the one hand, that's great, the key thing to keep in mind is that those life cycle assessments have pretty limited scope. So for example, the environmental, if we look at this as the life cycle of a building, the environmental product declarations really just cover this resource extraction and manufacturing, right? So just that part. The whole building LCA includes all those components, but then also the on-site construction. Whereas what we saw before is that, you know, depending on what you're talking about, 80–90% of the carbon footprint is often associated with the occupancy or use phase of the building, right? So that's a tension there. And as I said, I think it's a great start to have these things in LCA, but in LEED, but we'd like to try to shift that to looking at the whole life cycle. So. All right, so that brings us to our last element of this talk, and it's our objective to try to support early stage building design decisions with quantitative life cycle environmental impacts, and we're going to do that with a streamlined LCA. So what we really found when we did all these studies is that there's this chasm between quantifiable green building tools and designers, right? On the one hand, on this chasm, there's quite a bit of building LCA literature and tools, but on the other hand, you have architects and builders and developers, and most of them aren't using them, right? So even though they're modeling energy consumption, they're not taking that full life cycle perspective. So what we're trying to do in our work is to bridge that chasm. But I think part of what's going on here is that there's a tension in life cycle assessment that is a balance between the cost of doing a life cycle assessment and the credibility, right? And those, obviously you can have a low cost life cycle assessment, but it will likely have a low credible result, right? So the standard in building LCA right now is to do a high cost and high credibility approach. And so on the one hand, it's great to see people pursuing a high credibility approach, but the high cost is what limits it. Generally, what happens is that you need to generate what we call a bill of activities, and that includes a bill of materials, so the materials that go in, but also things like transportation distances, energy, and then you can multiply that times impact factors like global warming per kilogram of timber, or ozone implications, ozone impacts or acidification, and then from that we get the life cycle environmental impacts. Okay, and typically when that's done, as I mentioned, there's an energy analysis that's done, and the embodied analysis is done separately. But to do that, you need to start out with a description of the building, and then you need some type of approach to translate that description into all this data that you need in the LCA. And a lot of this stuff in the bill of activities is not necessarily things that architects need to do the designs. They're not typically generated. So the approach that we're developing in our research group is a streamlined approach. And what we're doing is trying to reduce cost while maintaining that credibility. And so we call it the building attribute to impact algorithm. And a key component of it is that the energy and embodied impacts are analyzed simultaneously. And a big reason for that is because we want to be able to look at these trade-offs between these different elements. And so what we do is we have a couple different ways that we get this to work. One is what we call attribute to activity models. And what we do is we take product attributes, like in this case attributes of the building, and then translate that into a bill of activity. So there are algorithms to do that for materials, for processes such as construction, and also energy inputs like electricity and natural gas consumption. We also have an approach that we call under specification, and this is basically using low fidelity and high uncertainty data. So rather than being very specific about what type of data goes into the model, we allow users to use pretty generic or underspecified data. So for example, rather than saying exactly what kind of wall system you're using, we just allow you to say, I'm going to use any kind of wall system. And then we account for the fact that if you're going to be that generic, that's fine, but we're then going to calculate impacts across the entire spectrum of wall systems, whether it be wood, steel, concrete, and then we'll capture the uncertainty of that. And obviously this is critical for use early in the design process when you don't have a lot of information. And last but not least, we have an element we call probabilistic triage. And that's just kind of a fancy way of saying you're just trying to identify what's the important data that you need with limited effort. And the importance of this is that it allows you to basically say, I'm going to start out with this underspecified data and be generic about everything. Then I'm going to let this triage tell me what's important, and then I'll do a deeper dive on that component of it. So how it works is that basically we start out with a user providing underspecified design information. So you can be underspecified on pretty much everything about the building and the materials that you're using. So underspecified on the size of the building, the number of windows, you name it, the orientation of the building, the type of roof. And then what we do is we run the model with a whole bunch of different simulations that account for that uncertainty. And those simulations are done using a Monte Carlo approach, which basically is what allows you to look at a whole bunch of simulations. Then you get a result that looks something like this. You get a total amount and a breakdown on how much associated with the use phase and how much associated with embodied impacts. And a key element is that it has this range of results. So the underspecification allows for that, but what we also get from the probabilistic triage is what are the top priority attributes. So in this case, we learned that your attic insulation and your roof deck and your window type are the top elements that are contributing to the uncertainty in this result. And as a consequence, you might want to be more specific about these. So provide more detailed information. So rather than just saying any kind of attic insulation, you may want to say, I just want to use bat insulation. And you don't even at that point even need to get into a specific R value. You can just provide a bit more specification on it. And then after you refine those priority attributes, you can then run the analysis again and see what kind of results that you get. And so this type of iterative approach, what it does is it allows you only to specify the things that really matter, and everything else you can leave generic. So when we compare these two approaches, remember that a conventional LCA will have high cost and high credibility, whereas what we're trying to do is develop low cost and maintain that same high credibility. So in more detail, basically, a conventional LCA approach has a high level of detail, whereas the BAIA, or the Building Attribute Impact Algorithm, has a minimal level of approach. Usually in a conventional LCA, you need a lot of details as inputs, whereas what we're using are what we call design attributes as inputs. Just tell us about the attributes of the building that an architect would consider, like I said, like just some things about orientation or window-to-wall ratios, things like that. In a conventional LCA, details are always specified, whereas in BAIA, you only need to specify details when it's really necessary for the result. A conventional LCA has to be used late in the design, whereas what we're doing can be used early in the design process. Usually a conventional LCA has energy and embodied analyzed separately, whereas what we're doing has them analyzed simultaneously. And of course, uncertainty is always quantified. And what we'll be doing is in a future webinar, we'll be getting into a bit more details on that particular streamlined approach. But like I said, this is just an introduction to it. So, all right, so in summary, what have we learned? Getting back to the research objectives we had, the first one was to identify what are the key drivers of building environmental impacts. What we found is that analyzing the complete life cycle is important. We found that in many cases that energy consumption is a particularly big driver, but it also can be of interest to analyze the embodied impacts as well. When it comes to the state of life cycle assessment in the building design process, we found that there's really a chasm between the tools and the studies that are available and the designers who might use them. And lastly, a streamlined life cycle assessment approach can be used early in that design process. All right, so what's the future of building life cycle assessment, at least from our perspective? Where do we think it's headed? I think the complete life cycle is going to become a more important element, not looking at embodied and energy separately, and I think that will also manifest itself in a more holistic approach to sustainability assessments. Right now, we have all these different topics in LEED analyzed separately, and I certainly understand why, but I think it we'll likely see in future versions of it a bit more kind of crosstalk among these different elements. I also see an integration of these types of approaches with the design process when they can be used early on in the design process. And lastly, we think that there's opportunities to incorporate resilience into life cycle assessment as well. If you attended a previous webinar we did on our work in the building space, you know that we have some approaches to account for that when it comes to costs, and I think that we're actually already starting to see some of this in the life cycle assessment space as well. So that's all that I had to present. You can find more information on our website or send us questions, and a few of the reports that I mentioned are available on our website there. And right now what we'll do is we'll open this up for a discussion because we got so many people, we've muted everyone, but there is a chat box where you can put in questions if perhaps some of you have already. And if you haven't yet, we'll just hold on the line here for a few minutes so that you can ask questions, and then Anne will read them to me, and I'll do my best to answer.
Thanks, Jeremy. We haven't received any questions yet, but hang out for a minute and just see if we do get any.
You got it. Sounds good. Like I said, just find that chat box.
And just as a reminder, we are recording the presentation today, so if you think of questions afterwards, you can certainly ask them by way of our social media channels or on the comment function for the YouTube video.
Absolutely. Absolutely.
Okay, so we do have one question.
Okay.
So when is attic insulation popped up as primary impact, is that the amount, when attic insulation is popped up as primary impact, is that the amount of attic insulation, the kind, or what?
It's generally, for that, it's going to be the type of insulation. And as you can imagine, so that, maybe I didn't mention, that study was for a single family building, and so the type of insulation, but it can also include the thickness as well, because obviously those are correlated. But both of those can be underspecified. You know, we obviously have limits on the ranges of what you can use, but we allow people to just say any amount and also any type of attic insulation. So it's a little bit of both.
Great. We have a couple participants that have raised their hand. I'll just remind and ask to please type the question into the chat window instead so we can read it out. So if you do have a question, the Q&A is up at the top right-hand corner, and like I said, just type it right in that box and we'll answer it. The next question that came in is just, well, it's a thank you. So this is a great presentation. When will it be available for use by a wider audience? And the answer to that is it usually takes us about 24 hours to get the video processed. So tomorrow or Monday, likely it'll be up on the YouTube channel. Any other questions?
Like I said, we'll hang out here for a minute or two to make sure people have opportunity to type them if they want.
Okay. So a question regarding the tools. When will the tool, the LCA tool, be available, or the process be available for a larger audience to use?
Yeah, I think what's going to make the most sense for us is that we have basically a version of the the tool that can be used for residential that I think we're pretty close to being able to share. What we'd like to do is try and find some partners to see how it can be integrated into a building design process, because I think that's what's going to make it more likely for designers to use it. Right now, I think if it's considered a separate analysis that has to be done, that's a barrier. So I think, you know, in the next few months, we'll be able to share a version that can be used as a standalone, and we'll be glad to be able to give that to people to play around with. But I think our next step after that is to start talking with a bit more and get a sense of what type of tools are being used in those early design phases and the degree to which something like this can be integrated into that.
Great, thank you. Next question, are you hoping to apply these assessments to other types of infrastructure, such as roads, concrete versus asphalt, or bridges?
Yeah, so we have been using life cycle assessment extensively for pavements. And if you look on our website, we have information about pavements and how they've been used for life cycle assessment of those elements. So absolutely, the answer is yes, yeah.
Another question, which regions in the world would you consider more advanced in the usage of such tools?
I think that what we see is that there's a big push in Europe for these types of environmental assessments. LEED is used all over the world. Europe has some of its own standards as well. There's BREEAM. And so, but once again, there isn't really a standard where, a building design standard where they mandate the use of a life cycle assessment. So I think that there's a lot of activity that's happened in Europe around the use of life cycle assessment, but I haven't really seen a place where it's become kind of like a core part of the design process. So I think it's pretty early stages worldwide in terms of actually being implemented in the design process or used in a design standard.
Thank you. Any other questions? That looks like it may be all the questions today.
Okay, great. Well, if you do have follow-up questions, like I said, we have our contact information here. We'd be glad to follow up and help you out.
Thanks, everyone, for attending.
Okay.